We'll probably get started in another minute.
Okay, so how did it went for you? The homework 3? Yeah. Okay, let's. Yeah. First question to you, Srinivas. Did you want to have some extra presentation today?
No, go ahead. I'll probably, you can take today and this session and the next. And if we have time in the next session, I think let's get into some code rather than more theory. And then, because anyway, the last part is not directly relevant. It's more, he sets it up for future discussion. So we can defer it until then.
Okay, cool. So, yeah. Homework 3, we will look at how to implement various kinds of variational autoencoders and kind of more modern flavors of it. And yeah, if you kind of looked through the various modifications of variational autoencoder, you saw that there are tons of those. And but here we start with a simple experiment. Let me get to it. So the task is following. We have a data, which is just a random sample from a Gaussian with diagonal, non-diagonal covariance, with a full covariance matrix, right? So the values like x's and y's here on the plot are correlated, as you can see. And we are going to model this distribution using variational autoencoder. And so precisely the task is following. We are going to model it with standard normal prior. So we assume so we have a prior which is normal with zero mean and diagonal covariance matrix with ones across the diagonal, right? And we will model the posterior with a decoder, which output with a which will output means and diagonal elements of the diagonal covariance matrix, and so with the encoder, and the decoder would also we will model the mean and standard deviation of the output distribution, right? So that would be the output of the decoder. It will be given x, provide me a or given z, provide me a parameterization of a distribution that generated x that produced that z value, right? So that's the goal here. So the training objective is like with variational autoencoder is an elbow. We try to minimize evidence lower bound, right? And we have two terms of this, and the one is reconstruction loss, and another one is the KL divergence between our prior distribution P of z and posterior distribution Q of z given x. And so let's look at what exactly the loss function would be in this case. So in general, for like standard variational autoencoder, the loss function will consist of following parts. It will be a reconstruction loss, which can be kind of any kind of loss function which is kind of relevant to the task. And we have this KL loss component, which is given here by this kind of a bit cryptic sum of four factors, right? And let's look at where this sum come from. So essentially what we have is some posterior distribution denoted here as P, and prior distribution Q. And we will consider the case for univariate, simple univariate Gaussian. And it will be essentially very similar for multivariate Gaussian with diagonal covariance matrix. So the KL divergence between two distribution P and Q here is like by definition an expectation under P of x of the ratio of logarithms of P of x and Q of x, right? And substituting the standard, the normal distribution for P and standard normal for Q, we can kind of unroll this into the following sum. So for standard normal, the variance sigma here is 1, right? So it will just the logarithm of 1 is 0, so it will go away. And we have some constants here coming from both distributions, which also cancel out. So eventually we will end up with like 0.5 expectation under P of x of negative log variance. So variance is a kind of variance of the posterior in our case. And here you see the x minus mu squared over sigma squared, which is a component coming from the posterior, like this logarithm of exponential, and this would be kind of a power in the exponential, and this one comes from the standard normal, so that would be mean equals to 0 and sigma equals to 1, right? Standard deviation equals to 1. So we want to take an expectation on the P of x of this sum, and that would be an expectation on the P of x of x minus mu squared over sigma squared. And as you can see, this expectation of square difference between the like data and a mean is a variance, right? So we have variance divided by variance, which gives us 1 here. And this part, you see expectation of x squared. And as you remember, the variance is equal to expectation of squared minus expectation squared. And by kind of replacing, so we can replace this term by variance plus mean squared. Okay, so does it, and that's our final KL divergence for like general normal distribution and standard normal distribution. So that's this four factors of it, and everything is multiplied by 0.5. That's Okay, and so in code that would be like this. Given now, so to compute the loss for variational autoencoder, we need the predictions, which are kind of whatever and targets. So those are the values we're gonna use for the reconstruction loss, and we add this scale divergent loss. For that we need the means and variances of the posterior distribution, right, outputted by the encoder in our case. And yeah, so this formula is for kind of univariate normal, but for multivariate normal with diagonal covariance matrix, basically these values would be just sum over all the components of the diagonal elements, right? But for the full covariance matrix, it would be kind of a bit more complicated, but we do not go this way. Actually, that can be done. So we can model the posterior with a distribution with non-diagonal covariance matrix, but it will just be a bit more computationally expensive. But yeah, there is a way to do it, and yeah, there is a white paper from Diederik Kingma and Max Wallin, which is called Introduction to Variational Autoencoders, and it contains the what would be the difference, what changes do we need to make to use to model the posterior with non-diagonal covariance matrix. Okay, so now let's go back to our kind of task here. So yeah, we will have this simple variational autoencoder for this task, and I've choose to use the encoder to be like 3-layer fully connected like 3-layer MLP, and decoder 3-layer MLP as well. And as you can see, the both, so the encoder takes X and outputs like two times dimensional of latent variable length vector, and the decoder takes in the latent vector, latent variable, and outputs also the vector of 2 times dimension of X. And why we have this 2 in the decoder? Because we're gonna output both means and standard deviations for the parameter as a parameterization of the distribution we're gonna model, right? Okay, and so the forward path of the model would be take X, put it through the encoder, we get means and log variance. We use a log variance here because like in this way we can output a full range, right? We don't need to, so the variance should be positive, obviously, like by definition, but by outputting the log variance and then taking an exponential of it, we can kind of avoid any complications related to the to outputting the full range. And obviously there are possible other ways. For example, you could like output some variable and then instead of like making it exponential, do soft plus or something else, like any kind of function that is has only positive outputs, but this way it's very kind of convenient for us, and you will see, because we need this value for the loss computation as well. So next, we reparameterize a random variable with this mean and variance. So the reparameterize function, it is here. So we first convert our log variance to the standard deviation, and for that we need to multiply it by 0.5 and take an exponential, and then we, like at training time, we will take a random we will sample random variables from normal distribution and multiply it by standard deviation and add the means. So that would be a reparameterization trick, which we kind of discussed, I believe, in detail in the previous sessions. And at test time, we do not add this kind of noise. We just use means, right? So that would be our latent variable. And then we feed it to the decoder, and the decoder outputs some so the decoder outputs values, and in this case we want these values to be the means and again log variances of another distribution which we want to model, right? And here I have this kind of conditional. So what we can output from the model, we can output this means and log variances, or we can output a sample. And to output a sample, we need just do the same kind of reparameterization, but with the means and standard deviations from the decoder. Okay. Yeah, and the last thing we can do with the model, we can sample. And to sample, we just get a random noise, basically, and we feed it to the decoder. And we have here this decoder noise parameter here. And if it will be true, then we will like repass it to the reparameterize method here. So then we have this do sample through here. And in this case, we output samples from the random, so from the normal distribution parameterized by mu and log variance. And if we set decoder noise to be false, then we just output the means predicted by the decoder. Okay.
Yeah, so yes. I got all that. The only question I had is why the multiplication by the 0.5 in getting the standard deviation back from the log var.
We get the log var. Yeah, the log variance is a squared square of standard deviation, right? So we can either output standard the variable, we can call it kind of log std, and then we will have to multiply it by 2 when we compute the loss. So here in the loss, we expect to have the logarithm of the variance, but so. And the logarithm is just multiple of one another, right? So the standard deviation is a square root of the variance, and the logarithm of standard deviation is equal to 0.5 logarithm of the variance, because the power goes to the multiplication. Okay. Yeah, so just you know, you have kind of a bunch of options how to write it, and that's kind of arbitrary choice I made, which might or might not be the most convenient way to do it. You know, because I've just took this 0.5 multiplier out of the brackets, but you can, as you can see here, this actually comes to first when you derive it, it comes to be just log sigma, and then you kind of can have it out of the brackets, and you will multiply by 0.5 only these three components. But yeah, just to get it into the brackets, you can add a square here and 0.5 here. So that's just the same value. Okay. Yeah. So that's what's going on here. And yeah, so let's keep that for now. And so I will just go by the like the process as I thought about it. So at first I've tried to model this distribution using mean squared error as a loss, right? So the mean squared error is an unbiased estimate of the likelihood for the normally distributed variable with a kind of constant standard deviation. So what will happen if we use a mean squared error as our loss here? So let's have a look at it. So this is kind of samples without noise we get from the model, and obviously it outputs the mean of the kind of the mean of the x for certain value, right? So if you check the input data, right? So we learn the mean, and if we enable the noise, we get this kind of not very noisy output, right? And now let's look at our other loss function choice we can make. We actually we know we are modeling a normal distribution, right? And therefore we can just compute the likelihood of the output under the normal distribution. We can use the parameters we produce to construct a distribution and compute the likelihood of the data under that distribution. So in this case, what the loss function would be? So this function, it computes the negative log likelihood of x under normal distribution parameterized by mean and the variance we provide. So we can use distributions module from PyTorch to compute this multivariate normal and at certain mean and for certain mean and covariance matrices we provide. And then we just, so we have our axis, the data, and then we can this function will output how likely the data is given this distribution, right? And the better the distribution we output it fits the data, the lower the loss will be, right? So the negative log likelihood. And if we use this as a loss function, so here we do kind of the same training procedure, but we have a different reconstruction loss here. And for this case, we have like here are noisy samples and here are the samples without noise, and you can see that without this decoder noise, so-called, we have again the same means for the distributions of our axis. But what we also learned the variance of this distribution, right? So we kind of assign to each data point here, we assign some variance as well. And that's why when we sample with this decoder noise, we get basically we get back the distribution we trained for. And yeah, so this is kind of, I keep the results from the which were provided by the instructors, right? So just to compare, and yeah, so my training curves are very similar to what they have here. Guess I don't know. Maybe I have. We can just to be sure. Let's check it here. 1 second. So here are the results from the instructors. Okay, so it's kind of, the numbers are similar. You see this 4 point something, 2.7, and 1.6. And I've got like even kind of better numbers, but that might be because different structure of the encoder and decoder. Okay, and then we can model another distribution with a different covariance matrix, and we will have the same results. Okay, so it did not converge this time for some reason. Let me see what's going on here. Okay. So you see that occasionally, for some reason, it does not converge. Maybe I've set, I don't know, a learning rate too high or something like that. But yeah. Oh, so those are the distributions with just with a full covariance matrix. And now we will try to model a distribution with a diagonal covariance matrix, right? So here you can see that we have just some distribution with diagonal covariance matrix, right? So the x's and y's here on the plot are uncorrelated, right? And yeah, let's try that. And you will see that here we have a very low KL divergence, but kind of reconstruction loss is something around the same numbers as we had before. And here you see that the samples with decoder noise resemble the distribution we had here. So you see that here it ranges from like -2 to 5, and from -20 to 20 something here, and basically it's kind of similar in our output, right? And you see that without decoder noise, we output just something that, and if you check it closely, you see that the range of the outputs is rather small, and it will be kind of close to the mean of this distribution, right? So because the like x1 and x2 are uncorrelated, what we can do, the best thing we can do for a mean, we can output actually a mean of the distribution. And you can see that what our encoder or decoder does. So, and the low KL divergence here basically means that our latent variable is very close to the standard normal. And why would that be? Yeah, and the answer is because our data so our decoder can model this distribution perfectly without any latent variable, right? This is a standard. This is a normal distribution with diagonal covariance matrix, and we are trying to model it with normal distribution with diagonal covariance matrix, right? And so our decoder can output this distribution with like the latent variable cannot provide any additional information to improve the outputs of the decoder. That is why what model does, our combined loss is a reconstruction loss and the KL divergent loss. And we cannot improve our reconstruction loss by forcing some structure on the latent space. That is why we just minimize the latent, we minimize the KL divergence component, and the reconstruction loss remains the same, so it is what it is. So does it make sense? So that relates to that point mentioned in the lecture. Then when you have a powerful decoder, your latent variable is likely to be ignored. So if the decoder can model the output perfectly without referencing z variable, then it will do just that, because if we cannot gain much in the reconstruction loss, but we can always kind of minimize the KL divergence, right? By setting the latent variable to be very close to standard normal. So that's what we have here. And yeah, the same pattern is observed for another variant of this normal distribution with diagonal covariance matrix. You see that the numbers on the y and x axis are different, but the shape is the same, and the means are really not meaningful. And you can see that the means are basically very tightly packed. So
also what this, just to put it in my own words, you see, the thing you mentioned is the more powerful decoder, or is it also the fact that the underlying distribution of X is normal, therefore the latent variable doesn't give you any more information and than what you get from just the input, and therefore the reconstruction loss is what it is, and the KL divergence loss is very low because the two distributions are identical or very similar to begin with?
Yeah, I think that the main factor is that our hidden variable kind of cannot provide much of useful information about the output. So, or in other words, it cannot not like so look, our loss here, let me try to find it. Our loss here it is just a likelihood of the data under the normal distribution parameterized with this mu and variance, right? And so basically, our loss function, we are not trying to match the data points exactly, right? We just evaluate how likely this data point is given this distribution. And so the distribution is like a normal distribution with diagonal variance matrix, and our decoder outputs a distribution with diagonal variance matrix. And yeah, therefore the latent variable cannot provide any kind of information to improve our output here over what we already have. Kind of in this case, so in the previous case, we had a correlation between x1 and x2, and that is why we outputted the decoder could output a different, given an x, we can output different parameterization for a normal distribution. So in this case, our output distribution, it depends on the x, right? And we can basically, if we are given x here, for example, we can output, we can model it with a normal distribution with a diagonal matrix, which is kind of centered around this point, right? But which basically it will be centered around the mean of this kind of distribution here around the line which you can draw here, imagine. But in case of normal distribution with diagonal matrix, let's scroll to it. So, for example, we are given a point here, but the best we can do, we can output a normal distribution with the same mean as this distribution and the same variance as this distribution to minimize the reconstruction loss. So the our x, it does not provide us any way to kind of narrow down this distribution, right? Because the values here are uncorrelated, and that is why our decoder learns to output the mean here, and it learns the standard deviation, which produces this kind of produces this distribution. But we cannot utilize our x as well as our latent variable, which comes from x, in any way, and therefore we just ignore it and put the KL divergence to minimum. Okay, I hope that kind of explains it. So that's my
that does. Now the only open question for me is I mean, that answer or that discussion completely covered it, but then you brought in the power of the decoder, which seems to not be directly relevant to this example, right? It's just, as you just pointed out, it's more the fact that the axis, or there is no inherent additional structure that the latent variable is able to deduce, and so there is not that additional stuff. But where does then the power of the decoder come in that you mentioned?
Oh, so the
at
power
least it
of
doesn't
the
in this
decoder,
case, or how does it?
Yeah, it's kind of related, I think, tangentially in this case. So when we have a very powerful decoder, as they mentioned in the lecture, right? So if you, for example, use Pixel CNN to model as the decoder, right? So the Pixel CNN can generate good images, right? So that is what we did with our first homework and first module, like say first module, right? We modeled the output distribution with the pixel CNN. And pixel CNN is capable of modeling the distribution of natural images quite well. And yeah, so in that case, latent variable can provide useful information, but it's kind of hard to balance the KL divergence component and the reconstruction loss in such a way that we actually the gain in kind of the increase in KL loss will benefit our reconstruction loss enough to enforce the structure on the latent space. Okay, and so yeah, that is kind of related tangentially, but yeah, to me it's kind of provides you some intuition. So if your latent variable encodes enough of valuable information, it will be used. If it doesn't have enough valuable information compared to the reconstruction, yeah, like compared to the reconstruction loss we get by enforcing structure on the latent space, then it will be ignored. So, but that's just my kind of speculation on the topic. Not do not take it to like for a pure knowledge here. So that's just yeah. And another thing I just wanted to kind of allude to shortly is this relation of mean squared error to the log likelihood under normal distribution. And so here you saw that, and why I'm kind of going to this, because we are going to use mean squared error as our loss function throughout this notebook further. But you can see if we are trying to model this distribution with using mean squared error, the best we can get is the mean, right? And basically to kind of understand what is going on here, I just wanted to look at the relay. So as I said, the mean squared error is like maximum likelihood estimator for the normal distribution with fixed variance. So if we take what would be the likelihood of X under some distribution, standard normal distribution, it will be so here is a PDF of standard normal, or not standard, but just normal distribution. And here is the logarithm of the probability of X under this distribution, right? So the logarithm of PDF. It has two components here. This one is kind of, contains the variance, covariance matrix, and the other one contains like the x minus mu squared divided by the variance if you interpret it as the unit variance, but that's just a matrix notation for the full covariance normal distribution. If we assume that the covariance matrix is diagonal, we get this we can simplify it. So this becomes a sum of x minus mu squared along the diagonal, right? So this is a vector, this is a diagonal matrix, and the product of this vector, diagonal matrix vector, gives us this sum over the components of the vectors. And the other thing is here is a product along the determinant of the covariance matrix is just a product of the diagonal components. So our final learning objective for this particular case becomes this one. So that is what we computed for this task here, that normal negative log likelihood, how I called that. And here you can see that we have something very similar to mean squared error, right? So this x minus mu squared will be, if we imagine the x is our data and the mean is output of our model, then this is just a mean squared error, right? But we also have this sigma here. And if you think about it, when we have like the average difference between x and the mean is large, then we can increase the variance parameter, and we get this component to be lower, right? So if we increase the variance, like in this case, variance is an output of our model. It's parameterized output of a model. So we can the model can learn it, right? And if we increase it, this component becomes smaller, but this component becomes larger, right? So we have a balance here. But if our distribution is tight, then this value will be low, and then we can decrease our variance estimate, and we with that we decrease this component of the loss function here, and therefore we can minimize it. In such way, we can learn both mean and variance in the example above, right? But if you exclude if you assume that the variance is constant, so it has no impact on our loss function, that the best we can do, we can just learn the mean of the distribution, right? So that what we saw when I was trying the mean squared error for this problem, right? So you see that the variance outputted by the decoder is set to be very low, because because what we can learn here is just a mean, and by minimizing the output variance of the decoder, we can minimize that component, the first component here, but we cannot do much about, because we can only learn a mean, we cannot do much here. Okay, so that is that's my understanding of what's going on, and this is related to what we will see here, and I think it might in some way explain the blurriness of the outputs of the variational autoencoders. And there is also another interesting, we just will briefly, let me just quickly find it. So I can just a second. just, yeah, I'm, sorry for the delay, and I think it was here. So here we have, yeah, this is a tutorial notebook from the deep learning course from University of Amsterdam. And here is kind of an example of failure of the mean squared error on certain images here. So have a look. So these two images here are just shifted by 1 pixel copy of each other, right? So this one is shifted by 1 pixel to the side here, like downward and to the right. And here is kind of the same image, but the first half is replaced with the mean color of this part, I guess, or something like that. And here is the same kind of pattern. And here is a mean squared loss computed on these two images. And you see that the mean squared loss for a shifted image is higher than a mean squared loss for the kind of image which contains no information, or like has half of the information completely wiped out. So that is kind of, and yeah, so that shows us that the mean squared error is not the perfect solution for this kind of problems, but it works somehow. But probably there is a lot of potential if one can use a more meaningful loss function here. And probably the GAN approach is one way to solve it. Okay, so now let's get back to our problem here. We are going to model the two data sets with images. One is SVHN dataset and CFAR dataset. Okay, and yeah, so we will construct a convolutional variational autoencoder here, given they even provide us some reasonable default configuration for the encoder and decoder parts here, that you can see that the decoder consists of the transposed convolutions, and the, yeah, so it kind of mirrors the encoder here, right? So we go from 32 to 16 to 8 to 4 here, and then project to the latent space, like a flat latent space using a linear layer, and then we just go backwards. We use a linear layer projection, then we reshape it to the kind of 3-dimensional input, and then we propagate it through transposed convolutions. And yeah, I think you might remember that we also have encountered some problems related to the transposed convolution in some courses before. So basically, when you do this transposed convolutions, they have some kind of aliasing pattern here, so that like the randomly initialized transposed convolution will not output a random image, but it will output some repetitive pattern. And yeah, if you don't know what I'm talking about, you can just ignore it, but that's just something also to think about, that you can construct this decoder in different ways, and probably there are alternatives to transposed convolutions as well. Okay, so Now let's have a look. So the data set is constructed. We are getting the images here, but actually what we want is tensor in a range between -1 and 1. So that is why I'm using here this toTensor function to convert. It converts from the images with pixel values from 0 to 255. It converts those to the float values in range from 0 to 1, and then we scale it to be between -1 and 1, right? And yeah, so that is our image data set, and when we will try to display images, we need to unscale those back, so that there is some utility function to do that. So the convolutional, simple convolutional autoencoder is just the same as regular autoencoder, but instead of using multi-layer perceptron for the encoder and decoder, we are using the convnet as described here. So we have convolutions followed by linearity, and then we have a flattened layer, and that will output our latent variable, and we use the same reparameterization trick as before. Yeah, so otherwise everything is just the same. Also notice that this time we do not, our decoder, it does not output the distribution, it is outputting a sample. So given X, we will output a corresponding sample of X, unlike before when our decoder was outputting actual distribution parameterization. Now we are just learning essentially we are just learning a mean, as I think they even say it in the problem statement. So yeah, we are learning here. You can see that the decoder, the probability of X given Z is modeled by a normal distribution with diagonal covariance matrix, which is assumed to be constant, and this is basically the mean squared error will be a maximum likelihood estimator for this kind of problem, right? So when we have a constant standard deviation and we are trying only to learn the mean, so that is relation of these two things here. Okay, and yeah, so yeah, let me just run it all. Oh, so if I just was talking to for a while, and the collab decided I'm not using it. That is not useful. Yeah, now let's train a model. We are using a kind of a bit modified mean squared loss here. We want to average across the batch dimension, but we are summing all of the other dimensions. So in this way, it's kind of valid probability of X, which depends on the dimensionality of X, right? So or log likelihood of X. And yeah, I probably need to decrease this one here, run it. So another thing to notice is that we can have another hyperparameter. So we can weight the KL loss component by some factor beta. And there is a couple of papers talking about that modification actually. And yeah, so that is called the beta VAE. And yeah, all that they introduce kind of in a practical sense is this hyperparameter, the weight of the KL divergence component. But yeah, they have like a lot of theory about how this impacts the kind of learned latent space, but that's probably what you need to put into the paper to get it published when your kind of contribution is rather small in terms of the network modification. So yeah, that's something kind of interesting. And another fun fact about
towards the end of the lecture, he talked about that as being I forget the name he used, but it seemingly helps you piece out the different well, I don't know whether I'm using the terms correctly, but different aspects of the latent space, so that, for example, you can change the color of the face independent from the hair of the face, independent from I don't know, smile of the face and things like that. So he devoted a couple of slides, and I touched on it towards the very end, that if you use exactly the beta and vary it to be greater than 1, the default being 1 for everything we have talked about, but if you make it higher than 1, then apparently it enables you to have the independent control of some of the latent variable parameters.
Yeah, so that's the theory part in that paper, and I think they speak about it, that this kind of enforces some particular structure on the latent variable. And I've actually, if you remember, we had the VAE part in the PyTorch deep learning course, and I've experimented a bit with it back then with this MNIST dataset, and I have some so what we have here, and that's another interesting thing to explore, the structure of, we can visualize the structure of a latent space. And by the way, you can see that when using a convolutional net as the decoder, our latent space is well separated even without even before any learning happens. So this is a visualization using TSNE algorithm, right? And yeah, and you will also observe this separation even when modeling the MNIST with a fully connected network, basically because even with random weights, you know, the different numbers tend to cluster together, right? Because of the connectivity patterns in the network. So that makes total sense, I guess. And here you can see that with training, basically what we are getting. So I think that TSNE is not deterministic, so it kind of visualizes this in somewhat arbitrary way. But you can see that with training we don't get much better separation here, but the latent space becomes more tightly packed. If you notice the axis, the numbers on the axis, and probably it would be nicer if I would do the like share Y scene. Yeah, I'll probably do it for the next session, and maybe we will go into it in with more details, and probably I will try to play around with MNIST more, because it's kind of really evident what is going on here, and then we can try to compare with different data set. So the C410. Okay, so and here you can see that with lower beta, yeah, so outputs are a bit inconsistent here, I guess. Not sure why. Probably the epoch 0 is the output after epoch 0, so it's not an untrained network. It's somewhat trained network anyway. And so there were some like hyperparameter difference. So you can see that here at epoch 0, it is not that well separated, but also what you can notice here is that the axes do not change much during training, and so the beta here was lower. So that is something to.
So is the beta 0.5 or something like that, Arto, for this one?
No, here it's 1, and in that case it was greater than 1. Oh. So I think I was going like from. Yeah, I haven't run this before this session, but yeah, that is kind of old stuff.
So the theory, yeah, so the theory is that if it is greater than 1, then you are getting better separation. So is that what you're observing?
Yeah, one thing is kind of better, not better separation, but I think a better structured, yeah. So if beta is greater, then the KL component is of the loss is higher, and our prior is forced to be closer, or not prior, posterior is forced to be closer to standard normal, and that is why it is more tightly packed. But if we decrease the beta, it becomes less kind of tightly packed here. And in terms of separation, I will have to kind of investigate this further, I guess. And
yeah, I misspoke. I shouldn't have said better separated. I realized as soon as I said it actually, and I haven't read that paper. I should go read it. But in the class, where the theory explanation that he gave, and not very detailed, is it helps independent control of the parameters, not that they are well separated as much as you are able to vary the latent variables along the dimensions independent of each other.
Yeah.
I don't know how that translates to a visual.
In other words, it can be like the latent space is well structured, right? So
yeah,
you can phrase it like the better structured latent space kind of better captures the latent underlying latent structure of the datum, right?
Right.
So yeah, but that is definitely something to explore further. And the very obvious practical implication of that is when we have a less kind of tightly packed latent space, our samples would be of lower quality because kind of it is more likely when we are sampling from the variational autoencoder, right? We just get a random variable. Oh, let's get just back to this. We take a random variable. Yeah, let's look through it here, for example. What we do, we just take a random variable we sample a random variable from random normal distribution, and then we feed it to the decoder. And the further our posterior is from a normal distribution, the less meaningful the samples would be, right? Because it is more likely to hit the like a blank space in our latent space.
Yeah. So it doesn't represent. It's unable to find the representation of the data, right? Meaning it's like being between the numbers or being between, as we explained in class, like let's say if it's a cat or a dog, then you get neither a cat nor a dog. It doesn't look like anything, for example.
Yeah. So if your latent space is kind of so another thing we will look at. So our network is probably trained, and let's just go through it, and we will discuss the phenomena as we go. So here you can see the learning curves, and you can inspect the numbers here. Yeah, another fun thing, I forgot to put this 0.5 in the loss before. Yeah, let me just get to it. So here you can see that when you derive, you have this 0.5 in the loss, and I forgot to just put it in the actual implementation. Here I had this beta, had this division by the batch size, but no 0.5 here, and I had to put the 0.5. I had to set beta to 0.5 in my experiments because so to match the results from the yes, in this homework they show their results for the first question usually. So that's fun. That really the impact can be strong of this hyperparameter. So that is interesting. Okay, and now we can have a look at some reconstructions we learned this time. So here the reconstruction is above, and the original image is above, and the reconstruction is below. And you can see that the reconstructions are really kind of blurry in this case. Maybe way too blurry. I think I had better result the previous time I've run it, but so it is what it is, right? And the previous time, I have this another set of reconstructions here. So notice here, you can see that you can, even though it is kind of blurry here, I think this 6 is kind of nicer than the original one, it's kind of better type. And you can also see some, so some of the input images are really blurry. It's the first place. For example, what is this? I don't know, and no surprise, a network kind of outputs what it got in. So that is something very similar to 7 or maybe 1. who knows? Yeah, and sometimes also, yeah, go on.
Go ahead.
Okay, so sometimes it also kind of, you can see that here the one is probably kind of well distinguishable, but the other number is kind of blurred out because maybe it is not in the focus or something like that, but you can see that the output is kind of, yeah, the second number in this from this two is blurred out. Yeah, so
yeah, I was observing kind of the same thing with the 37 versus, the 7 seems much more distorted than the 3.
Yeah. Yeah, so here it looks like maybe it's 1, right?
Yeah.
Okay, so let's look at the samples from the model. And it, for some reason, takes some time to sample. I don't know why it should be faster. So you see that the samples are quite diverse, right? So it's not like we have some mode here, right? As we discussed during the lecture. So the outputs from the variational autoencoder are quite diverse, right? So it's not like we outputting something with some preference here. Maybe there is a preference towards like having a number in the center, right? But probably that is kind of a good model of the data set we have. Right, but you can see that the colors are different, and yeah, we are getting kind of different shapes, but yeah, this is way too blurry to be useful, right? Probably, but also the underlying data set was kind of really blurry as well. And let's look at another interesting application. It is interpolation. So here you can see we will be interpolating between these two images. And let's get the interpolations. Yeah, so what is going on here? Like here we have a 9, right? Probably, I think it's a 9. Maybe not, maybe 8, but yeah, maybe 8. So probably it's 8. We have an 8, a blurry 8. And as we go here, we kind of switch from 8 to 6 here, right? So the idea of having a latent variable is that our model should output something kind of concrete, right? Not some kind of mixture of 8 and 6, but it should be either one or another. Like the in-between outputs should be meaningful as well. It shouldn't be like a linear interpolation in the data space. The linear interpolation in a latent space is supposed to produce valid data points at each of the linear examples. Let's have a look at another one because these are probably two similar. Let's just try something. Okay, we have 0 and 8 here, right? And yeah, this time probably because of quality of this 8, it's not. You see that we have 0, 0, 0, 0, 0, and here we probably have got something like an 8. Yeah, so yeah, that's how it works. And here we can inspect the results from, oh, those are my results first, probably. So here you can see the results from the trained model. And if you zoom out, this kind of looks better, right? because at kind of larger scale, you see this pixelization of the images, but if you make these things really small, then you get kind of better results. And yeah, so that's what we have for that question. And here is another data set. Okay, yeah, and I had a fun bug here. So I had kind of, with the notebook we have a state, and I had some variable set, like a wrong variable name inside a function, so that it was using a global variable in the notebook. And here is like these are reconstructions from the data points from the SHVN data set with a model trained on CIFAR10. so that is something really kind of fun happened here. And you can see that it reconstructs quite well. So these are only reconstructions. Here are no source images, only the reconstructed images. Yeah, but yeah, I've decided to kind of keep this scene here because I thought that this is kind of fun. You see, some images are kind of blurred out, but other ones are kind of, so here you can see we got kind of a good 5 or good 4, another good 4 here. So
it seems like even if your underlying data distribution is quite, and while there is some level of color overlap, right? Like, because even in your CIFAR stuff, you see some of the brownish colors, but you don't see too much of the black and white stuff. But it seems like even training on CIFAR and then inferring on your other, whatever the numbers data set, seems to be giving okay outputs, right?
Yeah, and you can, interestingly, you picked out this color theme. You can see some interpolations also printed here. And you see that in some cases, it kind of adds an unexpected color, right? So yeah, actually, I've looked at this interpolation and I thought, yeah, this is kind of not something meaningful, but then I realized that it is trying to interpolate the SVHN data from the and I think you see that it here kind of has but also another kind of speculative thought about this is following the CIFAR 10 dataset. It contains a wide variety of shapes, right? So the structure of the latent space we want to learn is really kind of complicated. It should have this. It should resemble the kind of a lot of structure of natural images in general, right? And probably that is why actually kind of you can think that this CIFAR 10 is kind of a superset of the other data set, right? So these are some natural shapes, and CIFAR 10 contains a wide variety of natural shapes, right? So
in other words, what you're saying is, the ability to capture the structure in CIFAR 10 should enable you to also easily capture should have given you the ability in the latent space to model the set of numbers, which is what you're doing when you're inferring.
Yeah, that's what. So I think it wouldn't work other way around, right? So the model trained on the numbers.
Yeah.
It wouldn't do any kind of even seemingly good job of reconstructing the natural images, because the underlying structure of this data set is much simpler and kind of restricted, right? But that is a speculation, but that is also something to try, probably.
Yeah, that's what I was thinking. It may, it's like just play with the reverse and train it on that and predict it on the sequence.
Yeah.
Or infer it on the sequence.
Yeah, we can actually do it, but I think I will do it off screen and report the results back to you. Okay, so that is yeah. So the CFAR 10 training. Let's run it. Okay, and yeah, let's move to the next part, and we will be talking about the variational autoencoder with autoregressive flow prior. And the idea here is that we don't have to model the posterior with, like, we don't have to assume that the posterior should resemble the how it's called normal distribution, right? In what we can do instead, we can use an autoregressive flow to project the latent space into the random normal variable, and then during sampling we can so why would we even do this normal prior in the first place? Because it enables us to sample, right? So if we have some complicated prior, it is good for the model, right? So the better the prior resembles actual structure of the latent space of the data set, or like describes data generating latent process, the better the model is. But we cannot easily sample from an arbitrary distribution, right? So what we like in the regular autoencoder, you also do encode the image into for example in an image into some latent space, and you kind of regularize it in some way, and then you decode the image, and you can get good results in decoding an image. But what you cannot do without this variational inference trick, you cannot sample from the any kind of regular autoencoder, right? So there is no way you can sample it. It can be just used to for the reconstruction of the image. You need a valid input data point to use it. But with variational inference, we can sample from a normal distribution, and then we can predict an actual data point based on the randomly sampled kind of random variable. And to make that work, we need some prior which we can easily sample from. And using autoregressive flow allows us to sample from a normal distribution. Then we apply, so the autoregressive flow is invertible. Then we apply, we can take a random normal variable, feed it to the inverse flow, right? And reconstruct our latent variable associated with the flow. and use that during inference. And that is what we are going to do here. So precisely, we will have the same kind of encoder and decoder, and the decoder will output, encoder will output the again the variances and means of some distribution, and then we will feed that latent variable to the autoregressive flow model, and we will map it to the normally distributed variable epsilon here, right? And the total loss function in this case will be, here we have a reconstruction loss, that's P of X given Z, right? And we have this KL divergence between our posterior distribution Q of Z given X and prior distribution P of Z. But in this case, we can express the P of Z as log P of epsilon plus log determinant d epsilon dz. So that is the change of variable trick used in flow models. And yeah, so that is what we're gonna do. And yeah, so I still have some bug in my implementation here. So we will go to check, so I don't show you some crap. We will go to check the reference implementation from the homework solutions for this task. And yeah, hopefully by the next week, I will have that implemented as well. So, and we will have a look what this variational autoencoder with autoregressive flow helps us to do. So first, what our flow will be? Well, the flow is modeled with a simple MADE. If you remember the first lecture, the MADE is autoregressive. So it is masked autoregressive model with a fully connected network, underlying fully connected network. And we will use like two hidden layer MLP to model to map our latent variable to the normal. So this is a normalizing flow. It outputs the means and variances, right? The flow we learn to output this means and variances, and then we reparameterize. Yeah, let's have a look here at the autoregressive flow variational autoencoder model. So we take an X here, feed it to the decoder, get the mean and variance of the latent variable Z. Then we sample, so we do the reparameterization trick and feed, we get Z, feed it to the decoder. So that will be our reconstruction. You see that the reconstruction loss is computed from that. Then what we do is that we compute the log probability of the latent variable Z under given distribution, right? So we sample Z with these parameters, and then we compute its log likelihood of the latent distribution. And after that, well, yeah, not necessarily after that, we just we have another kind of training route here. We feed our latent variable Z to the MADE, which outputs a mean and standard deviation. These are another two mean and standard deviation, and these are supposed to be, so we will just sample we will transform our variable z with this mean and standard deviation, and we compute the log likelihood of this transformed z under normal distribution. So here you can see it is very similar formula, but in this case we have mu equal to 0, right? And the variance equal to 1 of the expected distribution, and this would be like a log likelihood of the prior given this so log likelihood of the epsilon under prior distribution. So what it will allow us to do, so this is a invertible transformation, and during sampling we will get we sample a normally distributed random variable, right? And then we recursively feed it to the model. Feed it to the model. Then we take the ice component of the mean and standard deviation, which is conditioned on our latent variable, right? Then we transform it with an inverse transformation as compared to what we had here. So here you see the transformation is multiply z by the standard deviation and add mean, which is kind of equivalent to the reparameterization trick we did to our randomly sampled normal variable before. And here we do the inverse transform of that. And yeah, you should recognize, I think, those guys who were present at the previous practical session led by Mochan. You can recognize this pattern. This is an inverse transform of the previously done transformation to z, right? So by doing this inverse transformation to a random variable with parameters conditioned on this previous numbers here, we will get a mapping from random variable to the latent from a normal distribution to our posterior latent distribution. Okay, and that is our sampling process. We do it for n steps, or for dz steps. Yeah, so here we call it a latent size. So that is kind of autoregressive sampling, right? We need a previous value to sample the next value, and that is comparatively slow, but it allows us to. So what we achieve here, we take randomly distribute a random variable normally distributed, and we reconstruct, or so we do this inverse flow to our posterior latent variable, right? And then we feed it to the decoder, and supposedly we should be able to somehow get more kind of better samples from this, precisely more concrete samples. I would hope, at least for something that is more kind of concrete in this case. Yeah, so there you see the training procedure here is very similar to what we had in my implementation. So there is like a very standard training. Yeah, the learning rate is like typical 1 to the -3. And let's have a look at the results we get with variational autoencoder. And arguably we have a sharper sharper, how it's called, samples, right? And yes, and the reconstructions are very similar to what we had before, I guess. And well, at least that is what I would expect. Let's have a look what they managed to get for the reconstructions here. Yeah, I think the reconstructions are very, very similar, but the samples are kind of, yeah, arguably sharper, but yeah, it's hard to tell, right? And the interpolation, yeah, interpolations are okay, but you know, still not really that impressive. And let's have a look at the.
They seem sudden, right? Like, in fact, you know, the interpolations, they go 666 in the last line, and then suddenly, boom, 4444.
Yeah, and that is actually what you would like to have, right? Because yeah, because the so that is what we use the latent variable modules for, right? We want to again, if you remember one of the last lectures in the PyTorch deep learning course, when we had this kind of discussion about so the ellipse for certain value of x, you can get 2 points on ellipse, but you want to get a single point, right? And so I think that our latent variable should be able to kind of be reconstructed into a concrete data point. Yeah, so the sharper this
transition. Yeah, in fact, that what you just mentioned triggered even this VQ VAE that we'll get to next it's doing that, right? Because when it's somewhat close to the Gaussian, it wants to snap to the centroid, so it doesn't allow you to get to be in this intermediate space. It always wants you to be at one of the defined centroid spaces.
Yeah.
So it's like that, meaning that you don't want it to hang kind of between a 6 and a 4. You want it to be a 6 or a 4.
Yeah, true. So that is what we kind of trying to achieve, right? With the latent variable models, we want to get so a concrete samples, and you see that each of the latent variable models kind of has its own flow in this respect. So the variational autoencoders are associated with this blurry outputs, actually, right? So you can see that each reconstruction is blurrier compared to the original image, right? And it's still true for when we use an autoregressive prior, because it does not affect reconstructions actually much, at least from judging from the formulas. Okay, and as it was mentioned in the lecture, the GANs have this problem with mode collapse, so that they kind of output concrete sample or sharp samples, but they tend to output a very repetitive samples. So that is something. If you probably remember that example from the lecture end of the lecture with that range, where the GAN was outputting the kind of the same pattern, and the how it's called, the variational autoencoder was outputting different variations of the trench, like a single trench, a trench with a fisherman, or something like that. I'm not sure if I'm calling the fish right name, but I think you get what I'm
saying. But yeah.
And
so, there isn't that mode collapse.
Yeah. So, but on the other hand, I would guess that that comparison wasn't really, fair towards GANs. Like you always you see this pattern in the papers that yeah, you present the results where you get the results, right? Just as I do right now, I have presented to you what I've got working well in the homework, and now I'm switching to the reference implementation. Also, I haven't really kind of explored it before, but yeah, because my implementation didn't work as well. So, and that what people, that's what people do in papers as well, I guess. And yeah, so it would be really interesting to see what we can do with GANs in our next sessions and kind of try to find this more fair comparison.
Yeah, and actually he has, what in some sense, at least what I'm looking forward to is he has, I think, at least one lecture completely dedicated to just comparison of the techniques, which I'm assuming, he'll do a thorough comparison over 2 hours of all the different meaning flaws and strengths and weaknesses of each of the techniques we have seen after we look at GANs as well.
Yeah, that's nice. So let's briefly discuss the results from AF VAE on the CIFAR10 data set. And here you can see that the interpolations are, yeah, you kind of transform something blurry into something blurry, and again and again. And here, yeah, you transform something blurry into a sheep, probably. Right? But overall, or maybe that's a dog, or who knows. Yeah, but overall, you can see that it doesn't work that great on a more complex data. But on the other hand, yeah, that's some kind of, that's a model we can train on a collab, in half an hour or so. And yes, or for this model, we even need less time. Like it was something around 5 minutes for this training. So you probably shouldn't expect too much from that. And definitely, what we can we can try to switch. And we will use more powerful models for encoder and decoder for VAE. So we will replace their simple convnets with the resnets. And yeah, so maybe this can benefit from that as well, because, it's basically switching to a resnet gives you at least as good model as it was with a regular convnet, right? Because of if you initialize properly. So yeah, let's okay, I think we should defer the VQVAE discussion to the next session. We have basically we have one question left. The next question will be very related to the previous one. So we will look at how you get VQVAE to work, and then how you can model the prior for, or like the initialization, prior for VQVAE with pixel CNN. And then we will have a look on how to improve these models. And another, what I've kind of maybe not really entirely correctly, but alluded a bit in the beginning of our session, we will have a look at how you can use stronger decoder for VAE model. So we will have a look at VAE with pixel CNN decoder. And yeah, so a lot of interesting things to look at during the next session. Sorry. And yeah, but we don't have enough time to go to any of it in the detail. So yeah, let's have, if anyone has any questions, let's quickly discuss that. And maybe you had some insights or some questions regarding the homework implementations of the homework, if you tried that yourself, and or if you have any comments and maybe requests of what you would like to see for the next session. So there are lots of interesting variations of variational autoencoders. For example, in this Lian Wang's blog mentioned in the homework, she also has this TD-VAE. It's kind of interesting thing here. You can basically use a variational model to model kind of for the with together with RNN to for reinforcement learning. So that could be something interesting. And also there are applications of variational autoencoder to graphs and all the stuff. So if you would be interested in something particular, just I don't know, you can mention it on Slack or tell me now.
Yeah, the one comment, or at least for me, it was interesting. Over the last week, I listened to a robotics lecturer at some other open discussion, and it was fascinating to me. They actually use the autoencoders to have, so the problem they were trying to solve is, if the robot has a hand with fingers of, let's say, 3 fingers or whatever, and the question they were trying to answer is, what's the good way to grasp an object by the robot? And apparently the methodology they use is of taking pictures of the object and knowing your own, like, the robot has 3 fingers or 2 fingers or whatever. So they map both the object description and the whether it has 2 or 3 fingers into a latent space using autoencoders, and then play with it in order to get the best mapping by which the robot can grasp the object, which I thought was a fascinating practical application of autoencoders that, so far we have only seen it kind of in this theoretical.
And if you can post some references for that, we can kind of have a look at what's going on.
I'll see whether they post a YouTube or a link to that talk. It was in the main subject, but I just saw the application of autoencoders, which I hadn't seen in a real kind of practical application. So yeah, I definitely intend to keep my eye out. And if as soon as they post something on YouTube or whatever, it was for Stanford Open, and that professor is giving some course over the next, so it was kind of a pitch to
cool. Also, I
join
think
the course.
something the lecturer here, the Abil, right? He's working on reinforcement learning mainly, and in reinforcement learning for robotics. So he is the founder of this Covariant AI.
Right. But it wasn't Adil, it was a lady from Stanford. But I just thought, so far I'd only seen a lot of these kind of toy or at least theoretical developments applications, but that seemed to be a very practical application of autoencoders that I had not seen. I personally hadn't seen that, so I found that fascinating. I'll definitely post any links that I can find.
Okay, cool. Thanks. That would be really interesting to look at. Yeah, so also I think that the relation of the unsupervised learning and the robotics will be touched upon on the last lecture in this course. And also I believe, I don't know, maybe someone even posted it on our Slack, the talk of the Abil on the how they applied unsupervised learning for robotics. Also, they have a paper, like kind of, I think, a very interesting paper on that. Yeah, so hopefully we will get much more of robotics and unsupervised training kind of in this course towards the end. Okay, so it's
thanks a lot, Dato. That was very insightful.
Yeah, great. So thanks everyone for attending, and see you next week. And if you would like to...
sorry, I just wanted to mention next week is a break because of Labor Day in the US. I think our next meeting is on the 12th of September.
Okay, so,
as per.
I see. So then see you in 2 weeks, and so then I will have more time to prepare something interesting for you. And if you have any requests or questions regarding the, like, if you worked on the implementation of the homework and have some insights to share or some questions to ask, feel free to pin me on Slack. And see you.
Great, thanks a lot.
Bye, everyone.
Thank you. Bye.